My name is Patrick Chiang, an associate professor in electrical engineering. And today I'll talk to you about my research area, which is microsystems for wearables, and specifically, where does the energy go in these systems? So we try to understand the energy consumption for wearable sensors, both at the application level in the clinical setting, and then understanding in the clinical setting where that power is going to, how to minimize it at the VLSI and the chip integrated circuit level. So at the very high level in the healthcare application, we started this research approximately 5 years ago, working with Professor Tori Hagen in the Linus Pauling Institute. You can see on the left-hand side one of the patients in our clinical trial. We had 10 patients basically try to use lipoic acid in a 6-week double-blind placebo trial. And the conventional way for determining whether lipoic acid was efficient or not was having a blood sample once a week, which is very cost and cost ineffective. So we built this sensor, basically can monitor the heart rate and acceleration, and these elderly patients wore this for about 6 weeks. And you can tell that the biggest problem is this huge battery size. So, the PCB, of course, is not that nice. It's got, 5 chips with a BOM of about $50. But this battery cost and weight really prevented people wanting to wear this. So on the right-hand side, you see something what we're doing today, which is with off-the-shelf components, where now the battery is, of course, a conventional, very cheap 2032 battery. And this is basically used for measuring the EKG and pedometer reading for trying to reduce childhood obesity in a USDA clinical trial. And this is about 500 kids next year to run through this clinical trial. So these are using standard off-the-shelf components for basically about 10 to 14 days long-term use. But ultimately, we'd like to go to something that looks as big as this, to, of course, something that is a single chip, much lower cost, and hopefully 10 or greater times improvement in energy efficiency. And of course, this is probably very well known to Intel folks, because in the last week at CES, Brian Krasnick, your CEO, mentioned the Intel Curie SoC platform. And so, of course, these costs, these sizes are decreasing dramatically, but what's not decreasing, of course, is the energy efficiency as fast as these other parameters. And so along with just building the system application, we're building various analog and digital circuits to minimize energy efficiency, of course, operating at NTV, or near threshold or lower. So here you can see a couple of chips that we published at ISSC and other conferences, such as a low-power Bluetooth compatible receiver that we built with Professor Natarajan's group on about 1 milliwatt or less energy efficiency, which is about 8x less than a conventional Bluetooth. On the right-hand side, you can see some things where we did basically parallel processing in a wearable SoC. And even when you drop the voltages down so low, you get to things like soft error and reliability problems from radiation. So working with Dr. Vivek Day and Shekhar Borkar, we actually put this memory chip operating at 0.3 volts in Los Alamos to see what radiation effects had on this type of chips. So this is what we did in the past 3 or 4 years. More recently, we've been putting all these things into a single chip and try to tackle the problem of compression. So you've got so much data, but you don't want to use the Bluetooth radio. How do you actually compress your data without loss of reconstruction of your signal? And then finally, compression and then encryption, because authentication, security of your data is really important. So how do you actually put that in an area and power efficient way into your integrated circuit is what we're working on next.